Hi class, in this lecture here we're going to talk about differentials, and this lecture is going to be really important for the coming section. So this is going to be a somewhat shorter lecture than some of my previous ones, but I want to introduce some really important notation that you're going to see a lot when we move into integration. Okay, so what we're going to do in this section is we're going to find the differential of a function using differentiation formulas. It's going to be very easy. It's going to seem almost like a review. And then I'm going to do one quick example talking about comparing the values of the differential, dy, which I'll define in a second, with the actual change in y. All right, so let's begin first by talking about what exactly is a differential. All right, so in this lecture, we're going to introduce a notation that you're going to be seeing a lot in the next chapter when we learn about integration. And so given a function, y is equal to f of x, when we took the derivative of this, right, so y prime, we use this notation dy dx, okay? This dy dx, the dy and the dx are separate parts, and they're actually called differentials. Okay, and the relationship between them is given by the definition below. So if we let y equal some function of x, f of x, represent a function that is differentiable on an open interval containing x, the differential of x, okay, so this dx part, right, denoted by dx, is any non-zero real number, right? Think about it as like the change in x, right? Okay, then the differential of y, dy, is denoted by dy is equal to f prime of x dx. Think about it kind of like, well, not exactly correct. Think about it like this. Dy dx is equal to f prime of x, just cross multiply. And that's how you get this dy. All right, so let's talk about now very simply how you, if you're given some function or given an equation, how you find the differentials. All right, so for each of the examples here, I got 3. Let's compute the differential for each of the following. So we'll start real easy. We'll look at y is equal to 8x squared minus 12. So I want to find the differential of y, dy. Well, looking back here, dy is equal to the derivative of the function, f prime of x. So I'm going to take the derivative of this. We'll bring the 2 down. You get 16x times dx. And that's it. That's all you need to do here. All right, so dy is equal to 16x dx. Boom, we got it. Let's look at this one. Y is equal to 2x minus sine squared of x. I'm going to rewrite this as 2x minus sine of x squared. It'll help me. Okay, so dy is equal to the differential of y. Find the derivative. So the derivative of 2x is 2 minus, okay, we have to chain rule this. Bring the 2 down times sine of x, to the first power, that's good. And then the derivative of sine is cosine of x. And then dx. We got it. Finally, the third example here, let's look at this. Let's look at y is equal to x plus 1 all over 2x minus 1. All right, so you're going to need to use the quotient rule here. So dy is equal to, right, let's find the derivative of the numerator, which is 1, times 2x minus 1, minus, okay, the derivative of the denominator, which is 2, times x plus 1, the numerator, all divided by 2x minus 1 squared, and then dx. So let's just clean this up, right? Distribute the 1 here, 2x minus 2x, everything with an x goes away. Then you have minus 1 minus 2 times 1, so this is just minus 3 all over 2x minus 1 squared times dx. And that's just how, you know, you'll find the differential of y right there. Okay, and you'll get a chance to practice this, obviously, when you go to work on your assignments. All right, let's end by just talking about an application here, just so you can see how this differential of y dy equates to the change in y. So if we think of the change in x, or delta x as the change in x, then delta y, okay, is very, 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 very obviously equal to f of x plus delta x minus f of x. Okay, that just comes from, you know, looking at this. If you have some graph, this distance here is delta x. So then you know, this is x here, and then over here you have delta x plus x. This is f of x plus delta x. Down here is f of x. So you could see here then that the change in y has to be f of x plus delta x minus f of x. Obviously. Okay, this is the same thing we talked about when we introduced the concept of the tangent line. All right, this is the change in y corresponding to the change in x. Now, when delta x is small, so when the change in x is small, okay, we can assume that, or it becomes then that delta y is roughly approximately equal to the differential of y. All right, so let's use this information to find and compare delta y and dy and the differential of y when x is equal to 1, and delta x, the change in x, okay, is equal to dx is equal to 0.1. All right, and let's do this for y is equal to 0.53. All right, look. So delta y, what is delta y? Delta y is just this formula. F of x plus delta x minus f of x. Well, my f of x here is 0.5. And then what I'm plugging in for x is 1 plus delta x. So 1 plus 0.1 to the third power minus f of x, which is 0.5, and I'm plugging in for x here. X is 1 to the third power. So if you plug this into your calculator, okay, you'll end up getting 0.1655. Now look, what is dy? dy is f prime of x times dx. All right, well, what is f prime of x? You'd bring the 3 down, you'd end up getting 1.5 times x squared, okay, times dx. Well, if I plug in for 1 here, all right, and also plug in for delta x as 0.1, yeah, you end up getting 0.15 if you were to plug this into your calculator. So you can see that they're pretty close. They're pretty close. And what'll happen is as you decrease delta x, it gets smaller and smaller and smaller and smaller, closer and closer to 0. These two numbers continue to converge. All right, class. That was a quick introduction to differentials, but just keep the notation in mind. As we're going to use it a lot in the coming chapter.